Great stuff. Okay. Right. So this session, selecting protective devices, is really aimed at enhancing the last workbook I sent out to the group last evening, about 7 o'clock in the night, I think it was, by the time I got them all out. But it's basically this one. Okay, and the workbook does a pretty good job, to be honest, of highlighting stuff that normally crops up in the exam, how they're constructed, their typical ratings, their fault capacity before they're destroyed, applications, advantages, disadvantages for each of the types. So I'm not going to go over that. That's easily found, very easily found in the textbook. So 04A, you go through that, you'll find all that kind of stuff within the text. So it's simple reading and transferring within the workbook. I'm going to try and focus on the stuff that is sort of partially covered in the workbook, but not in the detail that I think is required. So I'm going to be looking at two aspects of selecting protected devices for overcurrent protection and how the regs sort of relate to that. So that's the purpose of this session. So the on-site guide, regs book, bits and pieces from both of those documents I'll be referring to throughout. Okay, the first thing I want to have a look at, and again, exam questions oming on this particular topic. Let me blow that slide up a minute. Overcurrent. Okay, the definition of overcurrent. It asks you for it in your workbook. Okay, and it's found quite simply in the regs book. You can actually Google it and find it. But it has a specific, very, very short, simple definition. So if that's pretty much word for word that comes out of part 2 of the wiring regulations. In fact, I've got the regs here in front of me. If I actually read out the definition, I think it is pretty close to that. It's very, very simple. A current exceeding the rated value. For conductors, this will be the rated value, the current carrying capacity of the cable. So the term overcurrent, very generic. There are really then two categories. One of them's a fault type current, and that's on the right-hand side of the flow chart. And the other one's not a fault in the wiring system. That's an overload. So the two types of current that you've got to, when you sort of start working through the workbook, make sure you get right, is the difference between those two categories. Fault current, there's definitely something wrong with the wiring system. Overload current is healthy. Is something wrong with the way you're using it? Okay, so an overload overcurrent is typically you've plugged too many things into a ring circuit. You're trying to operate a device on a circuit breaker that's smaller than the actual design current. You're overloading an otherwise healthy circuit. Fault current, completely different. So this one tends to be times 1.5, times 2 current, you know, small amounts of overload current. And they can be the worst because they can sustain on the system, as you'll see later on, for long periods of time and cause damage. Whereas your fault currents, your short circuits, your earth faults are going to be of such a magnitude that they clear the fault quite quickly. So a fault current is a current resulting from a fault, and that fault is then split into two further categories. A short circuit, okay, is absolutely not to earth. The regs make it clear, although we term it that way sometimes, it's between live conductors. So on a three-phase supply, L1 to L2, L1 to L3, L2 to L3, any of those lines to neutral, the neutral's a live conductor. On a single phase supply, it would be line to neutral. Whereas your earth fault current is between line conductor and exposed conductive parts. So the one that we looked at this morning with the earth fault on the panel heater, line to earth. Okay, and these faults on the right hand side are faults of negligible impedance, so there's no resistance, we hope, limiting the amount of current, because we want, and the right hand side, we want lots of fault current to flow to operate the protective device as quickly as possible. Okay, so those are the definitions, okay, that you're looking at, you're finding, and putting in the beginning of the workbook. And these are just some images, so I can get it in your head before we have a look at fusing factors of typical devices that you have to refer to within the workbook. So these are BS88 cartridge fuses, often called industrial fuses, tab type ones. Sometimes they haven't got tabs on them, sometimes they got screw tabs on them. Okay, so typically domestic cutout fuses would have either had a BS1361 or a BS88-2 type. This fuse on the right hand side was the fuse that was sort of pretty much invented or created in that format to replace these original rewirable fuses. So these are just fuses with bits of wire semi-enclosed. These are the equivalent enclosed. Okay, they were BS 1361, but they got redesignated in the 17th edition of the wiring regulations to BS 88.3. But they go by the names of cartridge fuses, link fuses, industrial fuses, rewirable fuses, semi-enclosed fuses. But it's these numbers that you've got to learn. Okay, so again, you'll spend a little bit of time on the workbook becoming familiar with those, and now we've got some resettable overcurrent protective devices. So your typical circuit breakers, single pole, double pole, triple pole, a molded case circuit breaker that you get in industry, you know, hundreds of amps, thousands of amps, same sort of operating principle really. And then you've got these devices that are part RCD and part circuit breaker. So residual current facility with overcurrent breaker protection built into it. So these are all what are now recognized with the abbreviation OC, overcurrent, PD, protective devices. Okay, they all deal with large current faults. And the other thing the workbook asks you to have a look at is the breaking capacity, not the operating current of the devices. That's something we're going to look at now and is completely different. This is the amount of current a particular device can handle without its characteristic being changed, it not being able to function properly in the future. Okay, so you'll see by looking at that screen, the best current handling is provided by HRC fuses, high rupturing capacity fuses. They're the ones that you typically find in cutouts at the origin of a supply. They can handle up to 80 kiloamps, some of them, and the worst are our rewirable fuses. They were as low as 1 kA, 1000 amps of fault current. So you definitely needed something upstream of it to be able to handle certain currents. So there's a range of breaking capacities that different devices could handle. They're sometimes printed on the device in that way, 6000, M6, there's an M3 or 3 kA. All of those things indicate its breaking capacity, what it can withstand without damage. Okay, right, now we're going to go back to the workbook. Okay, and one of the things that the workbook looks at is a fusing current, but it doesn't spend too much time on it. And it's actually an important thing. It leads into some of the stuff we're going to do tomorrow morning on circuit design. So what I want to do is show you an extract from the wiring regulations, Appendix 3 of the wiring regulations. I don't know if any of you've on any courses, if you've done a regs course, hopefully this would have been something they looked at with you. That's what's called a time current graph. It's for BS88.3, so cartridge fuses, this particular one. And this particular one covers 8 types, I think it's 8, yeah, 8 types, 8 ratings of device. So between the 5 amp and the 100 amp device. And what it allows you to do, this is a generic one, it's not by a particular manufacturer. You will find manufacturers, more detailed ones on their own website, like Hager, Wilex, Crabtree, etc., etc. But what it allows you to do is to actually, by studying it, learn a little bit about different protective devices, how quickly they operate. So what I want you to do is, first of all, realize it's an odd scale. It's what's called a logarithmic scale. 1, 2, 3, 4, 5. You can see as you get towards the upper range, they get closer together. And likewise, 10, 20, 30, 40, 50 is not halfway. And these portions aren't like 10, 20, 30, they're not equal amounts. It's to enable you to get a large amount of data, like in the 10,000s of amps, in the 10,000s of seconds, you know, 3 3/4 hours, 10 kA, onto a small A4 sheet of paper. That's the scale. So you've got to get your head around the scale as you're sort of reading things off of it. But basically, the ones that we're going to look at have time up the left-hand side in seconds, current, fault current, prospective current, whatever you want to call it, in amperes along the bottom. And then we've got 8 typical ratings of cartridge fuse. So what I want you to all have a look at is, I'll give you an example now for this 5 amp fuse, typically one that might be used for a lighting circuit. So like a white cartridge fuse. If 10, hang on, let me get my highlighter pen down a minute, so you can definitely see what I'm highlighting on. If 10, 20, 30 amps was to flow through that 5 amp fuse, can you see that fuse would operate in 0.1 of a second, a tenth of a second, with a current of 30 amps flowing through it. If 10, 20 amps flowed through it, so a fault current of only 20 amps, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6 of a second it would take. Okay, with about, for it to operate in 1 second, it's going to be kind of about 27, 28 amps. So do you see how it works? So what I want you to have a look at is for the 16 amp one. So this second curve, can you have a look and see if you can see for a fault current of 100 amps, how quickly that device would operate? And if I can ask Chris to unmute and have a go at the answer. 100 amps into the 16 amp fuse. I'll unmute you, Chris.
0.3 of a second.
0.3 of a second, well done. 100 amps. 0.1, remember that's the baseline, 0.2 and 0.3. It's so easy to pick 0.2 there and get it wrong. I mean, you could have got a bit of an estimate by having a look at this associated table. For a 16 amp fuse, it takes 110 amps to operate it in 0.2 of a second. It takes 95 amps to operate in 0.4 of a second. So our 100 amps that I said is somewhere in between the two. So it's a good sort of double check that you're pretty close to the answer. These are typical questions that come up in the 04A exam or the regs, 18th edition regs. A different type of but similar question is, what current would be required to operate that same 16 amp fuse in 0.4 of a second? So now what current is required to operate that in 0.4 of a second? And Danon, if I ask you to unmute and have a stab at that one.
I'm going to say 95 amps, roughly.
I've got written down as well. Yeah, it's a little bit sort of kind of like how closely and how accurately you read a logarithmic scale, but basically the procedure is 0.1, 0.2, 0.3, 0.4. We're somewhere between 90 and 100. Okay, as you'll see on this scale, halfway between 1 and 10 isn't actually 5, it's more like 3. So it's quite likely that it's smaller. But again, if you'd come up here, you could have seen that it does actually take 95 amps. The table, you know, makes it for this particular question bang on, like 0.4 of a second. And finally, what I'd like you, before we move on to another graph, is for that same fuse, what's the minimum current that will actually make it operate at all? The minimum current that will make that one operate. And that question, Sean, if you want to have a go at that one, what's the minimum current that would cause that 16 amp to operate? It's a bit debatable, but do you want to have a go at that one, Sean? Unmute yourself and come in with that one.
I'll give it a go, mate.
Somewhere where I'm hovering over. Round about there. There's your 10 amps.
I'll go with 25.
Okay.
Maybe, give or take.
I went with 23, but only because I know better. All right. But if you read it off that scale, it looks about halfway. But again, if you come back to here, you can see that halfway is about 1, 2, 3. So that's how I know it's closer to 23.
Roger.
Okay. And what you can see from that, if 23 amps did flow, the minimum current, it would take about 3,600. And again, I know that to be a fact because I've done the experiment with a 16 amp fuse, and it does take 1 hour. Okay, so what this should tell you is two things. Fuses and circuit breakers never, ever operate on their rated current. They're designed not to. If they did, they would be faulty. And in fact, you can see that for this type of device, a 16 amp cartridge fuse, it actually takes 23 amps. And from those two values, the 23 amps of minimum operating current and the 16 amps rating, you can actually work out what's termed historically the fusing factor. You just literally divide that 23 amps, anybody who's got a calculator on them or a phone with a calculator on it, if you divide that 23 amps, which is the minimum operating current, by its rating, okay, so 23 divided by 16, I get rounded up 1.44. Anyone else nodding to agree with that if you've had a go?
Yeah, 1.44.
1.44. Okay, so that's the fusing factor for BS883 type devices. Okay, it takes nearly 1.5 times its current to actually operate it, and then it takes an hour for that to happen. So you've got to have a substantial current going through it, all right, for it to operate quickly. We'll whiz through and we'll have a look at the 1-4 circuit breakers. There's 3 of them for type B, the ones we use in a domestic environment, type C and type D. So this is a slightly different looking one for circuit breakers. Okay. But again, if we look at a 16 amp circuit breaker, okay, can you tell, first of all, going in reverse order now, about what minimum current it will take to operate it at all? Look where it's coming down, and this question's for Ed. It's coming down.
Oh, 21. 21.
That's close. Let me see how close that actually is, Ed. 21 divided by 16. It's closer to 22.
Okay.
In fact, it's closer to 23. Let's do it again then. If we come down here, it's about a third of the way along the scale between 10 and 100, a third along the scale. 1, 2, 3. Yeah, it's closer to 3 than it is. So 23 amps. Now, if you divide 23 by its rating, 16 amps, you're getting pretty much the same again, 1.437. So what you can see from these 2 types of devices is that basically they've got a very similar fusing factor. Now, if I slip back to the bad boy of the protective devices, this is your rewirable fuse. This is the one that's still in my dear old mum's house that was wired in 1967. 4-way fuse board, red one for the cooker, red one for the sockets, blue one for our immersion, which is now a boiler supply, and a white one for all our lights. And that's the way it was when it was wired to the 14th edition. And that's the way it is now, because nothing's changed. You wouldn't believe her eldest son next to kin was an electrician. You don't go blowing your inheritance on things like electrics. So basically, her premises still uses this. The regs quite clearly, because this is right out of the 18th edition, still recognizes them. They can be left in service. But this is what, as electricians, if we are considering, like someone did for our immersion, because it was ripped out and a combi boiler was put in, reusing that, what actually is a 15 amp device, you've got to bear something in mind when you're looking at the cable that you're protecting. There is nothing wrong with a rewirable fuse. They're foolproof. If they're not fiddled, if they're not, you know, wrong size fuse wire put in them, they melt when they get hot. Circuit breakers got 46 moving parts in it, and they do go wrong. So there is nothing wrong with them. They were the first protected device, and they still are the foolproof one, except this is the problem. Look, if you can, to see for the 15 amp, because there's no 16 amp version, it's 15's the closest. Look down through on that scale now and see if you can see what current it takes, minimum current, to operate that protective device. And that's one for David. What do you reckon that is, David? Are you there, David? Unmuted yourself? No? Okay, I'll ask Mark to come in then. Mark, what do you reckon that value is in current for the 15 amp device?
28.
Yeah, it's really up there, isn't it? It's getting close to the 30 amp line. I would say on this scale here, it's probably about there. So I would say 29 amps. And if you divide 29 by 15 amps, the device rating, you get a fusing factor of 1.9333, which is actually in the regs rounded up to 2.
Right.
Okay. So of all the protective devices that we now use, cartridge fuses, circuit breakers, okay, they all have somewhere between about 1.4 and 1.45 fusing factor. And it's that fusing factor that's taken into account when tomorrow morning you see us selecting cables. All the cable ratings in the on-site guide, manufacturer's sheets, the wiring regulations, Appendix 4, all the values, like for instance, a bit of 2.5 twin and earth has got a rating when click direct of 27 amps. That 27 amps takes into account that you could be letting through 1.45 times the rating of the cable. So 1.45 times 27 is 39 amps. So this cable, although they don't tell you that, can actually handle 39 amps indefinitely. But we don't tell you that simply because you take advantage of that. But if you've got a device that only lets through that amount of current, it will handle it indefinitely. Now, the problem lies here with the rewirable fuse, okay, or semi-enclosed fuse, 3036 fuse, whatever you want to call it, that's got a fusing factor of 2. So that means that little overload factor that has been built into cable current ratings will now be exceeded, is likely to be exceeded, because these things don't operate really until twice their rating. So typically a ring circuit protecting a 2.5 mil ring circuit would let like 60 amps through. And that cable, even the combination of those cables, 2 times 27, 54 amps, can't carry that indefinitely. It would overheat, temperature rise, melt the PVC. So what the wiring regulations make you do is take that factor into account. And if you do want to carry on reusing a rewirable fuse with some circuit that you're modifying, adding to, or whatever, then what you do is you build a factor in. It's called a CF factor, a fusing correction factor. And what they make you do is take the value of 1.45, which is the fusing factor for most modern devices, and the fusing factor for the rewirable fuse that you want to carry on using, and divide one by the other. So you take the 1.45 and you divide it by 2. The 1.45 fusing factors of, say, for instance, a circuit breaker or a cartridge fuse, and you divide it by the fusing factor of the rewirable that you want to use, and you get a value of 0.725. Now that's the value that you will find in the wiring regulations that you must apply to all cable ratings if you want to continue to use that type of fuse. So for instance, if you've got a 2.5, it's a radial circuit supplying an immersion, and you want to convert that, we're taking the immersion out, but I don't want to lose the circuit. I want to put a double socket in its place. Nothing wrong with that. Stick the double socket in, but recognize you will not have a current rating of 27 amps that you would get, because that's what the tables say for 2.5 click direct, 27 amps. What you'll now get, because you want to use that rewirable fuse, is 27 times 0.725. You can only get 19.5 amps out of that cable. So you now have got to make sure you put typically a 20 amp or 15 amp fuse to protect that cable. Okay, so in summary, because we've got about 5 minutes left, in summary, fusing factor, it's an historic term, okay, because it comes from the old days of fuses, but it does apply to all overcurrent protective devices. Okay, it's the relationship between the minimum operating current of the device and its rating. So typically, as we've just seen, 30 amps minimum operating current for a 15 amp fuse divided by 15 times 2 factor. Okay. And for a rewirable fuse, if you want to continue using that in service, you must then apply a 0.725 factor, a CF factor, in your circuit design. And we'll pick up on that tomorrow morning when we have a look at circuit design. Okay, right, we've got a few minutes left. If you want to unmute yourself, if you've got any questions about any of that. Okay, what I'm trying to do, just to update you, I'm trying to make sure that I get these videos online on our VLE within 24 hours. Sometimes I'm getting them done before the following morning, but it is quite a task, quite a process we've got to go through to get them sort of published. But they're going to be there, you know, by the end of the week. If you need to go back over any of these, they're going to be there. There's a password which I did publish at the beginning, but just in case anyone new hasn't got that password, what you basically do is just a reminder, because I've got a bit of time. You just Google basically PGL training. Okay, PGL training, not just PGL, and it takes you to that page, and it's the far right hand tab, the VLE tab. And then basically it will now show you something that looks like this. Okay, so it's got the video. Today's video will say session 3, session 4 even. And the code that you need the first time at least that you go in is that capital letters PGL 900 #9. Okay. Any question, guys?
All good for me.
Brilliant. Okay, well, nice to go through that with you again. Tomorrow's 10 a.m. Zoom meeting will be to do with circuit design. And again, I shall be later on this afternoon, early evening, sending out the resources for that. Okay.
Brilliant.
Have a good
All right,
rest of
thanks,
your
Chris.
day and see you in the morning, hopefully.
Cheers.
Cheers,
Thank you.
Chris.
All the best.
Thanks.
See ya.
Bye.